Welcome to this explainer. We're jumping right into a notorious challenge from the Class 11 mathematics curriculum today. Specifically, we're looking at Chapter 3, Exercise 3.1, Question 5. Now, if you've opened your textbook to this exact page recently, you might have felt a mild wave of panic. It's a classic 5-mark question that looks absolutely intimidating at first glance. But seriously, don't worry. I promise we're going to make this incredibly simple. By the time we wrap up, you'll see exactly how to break down this complex problem into really satisfying, bite-sized logical steps.
So here is the absolute monster of an equation we're up against today. We're given this: cosine to the power of 4 alpha over cosine squared beta plus sine to the power of 4 alpha over sine squared beta equals 1. And from that single, messy line, we have to prove two entirely separate identities. What makes this look so terrifying is that crazy mix of fourth powers, squared terms, and different angles. All those alphas and betas just stacked on top of each other in fractions. It looks like a total trigonometric nightmare, right?
But let's take a collective deep breath, moving right into section, the substitution strategy. Instead of getting totally lost in a maze of complex trigonometry, we're going to use a brilliant workaround. We're going to temporarily strip away the trig entirely and turn this beast into basic algebra. Notice how elegantly we can map these complex terms to super simple variables. Let's just declare that sine squared alpha simply becomes x and sine squared beta becomes y. Simple enough. But what about those cosine terms? Well, thanks to our old friend, the fundamental Pythagorean identity, sine squared plus cosine squared equals 1, the cosine squared terms naturally become 1 minus x for alpha and 1 minus y for beta. Just like that, the messy trigonometry totally vanishes. Okay, let's plug those incredibly clean algebra variables back into our original monster equation. Since cosine squared alpha is 1 minus x, well, that means cosine to the power of 4 alpha is simply the quantity 1 minus x squared. Similarly, sine to the power of 4 alpha just becomes x squared. Put it all together and our brand new equation is 1 minus x squared over 1 minus y plus x squared over y equals 1. Take a second to look at that. Doesn't that look a million times more manageable? It's just an algebraic equation now, completely free of alphas, betas, and any trig functions.
Now that we've got our clean algebraic equation, it's time to actually dig into the math. Section, proving the hidden truth.
We are hunting for a secret relationship hiding right beneath the surface here. First things first, we'd normally need a common denominator to add those fractions on the left side, right? Which would be y times 1 minus y. But honestly, to make life way easier, let's immediately skip to cross-multiplying so we can just eliminate those denominators completely. Flattening the equation onto a single line gets rid of the fraction headache entirely. This leaves us with y times the quantity 1 minus x squared plus x squared times the quantity 1 minus y equals y times the quantity 1 minus y. Let's carefully expand this whole train out. We expand the perfect square, 1 minus x squared, into 1 minus 2x plus x squared. Next up, we distribute our variables across all the brackets. So the equation stretches out to y minus 2xy plus yx squared plus x squared minus x squared y equals y minus y squared. Now look incredibly closely at this next part. This is one of those deeply satisfying moments in math where things just magically fall into place. We have a positive yx squared and a negative x squared y. They are the exact same term, just with opposite signs. So they literally just cancel each other out, giving us some massive momentum. Let's clean up whatever is left over. Our simplified line is now y minus 2xy plus x squared equals y minus y squared. Notice that y floating on both sides of the equal sign? We can just subtract y from both sides and poof, they disappear. We're left with x squared minus 2xy equals negative y squared. For our final maneuver, we just pull that negative y squared over to the left side and boom, we've rearranged that whole messy equation into a beautiful perfect square trinomial, x squared minus 2xy plus y squared equals 0. Which, as we know, factors perfectly down to the quantity x minus y squared equals 0. And that right there brilliantly illustrates the absolute core truth of the entire problem. If x minus y squared equals 0, well then x must equal y. There's no other way. And if we think back to our original substitution, we've literally just proved that sine squared alpha is absolutely identical to sine squared beta. This is the hidden truth. The entire complex equation they threw at us at the start was just a really heavily disguised way of telling us that these two squared trigonometric values are exactly the same thing. Armed with this newly proven superpower, the rest of this 5-mark question is going to be incredibly straightforward. Section, Comparing Part 1. Okay, Here is the very first requirement the textbook throws at us. We have to prove that sine to the power of 4 alpha plus sine to the power of 4 beta equals 2 times sine squared alpha times sine squared beta. Remember, we literally just discovered that sine squared alpha and sine squared beta are totally interchangeable. So the question is, how can we creatively apply our x equals y discovery to solve this in seconds?
Check out this lightning-fast logic. Let's start with the left-hand side. Because our truth states sine squared beta equals sine squared alpha, we can just swap out the beta term entirely. So the left-hand side becomes sine to the power of 4 alpha plus sine to the power of 4 alpha. Add those up and you get 2 times sine to the power of 4 alpha. Easy. Now over on the right-hand side, we have that 2 sine squared alpha sine squared beta. Let's just substitute one of those alpha terms back into a beta. By strategically swapping these identical terms, we force the left-hand side to perfectly exactly match the right-hand side. Part 1 is completely proven, just like that.
You guys are doing great. Awesome focus so far. We've knocked out the first half of the proof, so let's keep this energy going and pivot immediately to the final challenge of the exercise. Section Conquering Part 2.
Here's our final boss for part 2. Prove that cosine to the power of 4 beta over cosine squared alpha plus sine to the power of 4 beta over sine squared alpha equals 1. Now, notice anything a little familiar about this? It looks almost exactly like the original monster equation from the very beginning of the explainer, but all the alphas and betas have been flipped. The denominators are now alpha and the numerators are beta.
But once again, our hidden truth is going to save the day here. Recall the golden rule we found. Sine squared alpha equals sine squared beta. Naturally, because of how trig works, this guarantees that cosine squared alpha also equals cosine squared beta. So, focusing on the left-hand side, we can just replace those alpha denominators directly with betas. Our equation transforms beautifully into cosine to the power 4 beta over cosine squared beta plus sine to the power 4 beta over sine squared beta. Because they match now, the division cancels out the powers perfectly. We are left with simply cosine squared beta plus sine squared beta. And thanks to the absolute most fundamental identity in all of trigonometry, we know that always equals 1. Part 2 is fully proven. Which brings us to a massive golden rule for your upcoming exams. When trigonometry gets too messy, let algebra do the heavy lifting. We started this explainer with an incredibly intimidating, messy fraction filled with huge powers and mixed up angles, but by substituting variables and just flattening it all out, we found the super simple truth hiding underneath. I really encourage you to always look for the simpler algebraic structure hidden inside intimidating math problems. It is almost always there waiting to be found. So as you look back at that original monster equation, I leave you with this final thought to chew on. What other terrifying formulas in your textbook are actually just simple algebraic truths wearing a complicated mask? Keep hunting for those hidden truths, and thanks for learning.